Welcome to Mechanics of Composite Materials. Today we'll be learning how to apply failure theories to a practical problem, and for that I have invited George Halamandaris that will guide us through this tutorial, and we'll be learning from him. So thank you so much.
Welcome everyone. Today we will be going through a tutorial on classical laminated plate theory as pertains to failure theories. A little bit about myself. My name is George. I am currently a senior vehicle engineer at Virgin Orbit, as well as a master's student at USC. So let's dive into the problem. So we'll have a plate with a given layup that has force and moment resultants applied at the edges. So we are going to develop a code that is able to determine the ply-by-ply stresses and strains and evaluate those as compared to the allowables for the material to try to inform our design and predict failure. Today we'll be working with AS4-3501 unidirectional carbon epoxy. As you can see below, the tensile and compressive strength allowables in the longitudinal and transverse direction are given, as well as shear, as well as the modulus, Poisson's ratio, and ply thickness. For this application, we are given an N tensor with different load values, and the A variable will give us an opportunity to vary those loads, which will be the stress resultant. It's important to consider units in this application as opposed to a direct force on the edge of the laminate. This will be in line load, and then as well as this is a moment resultant, so moment per inch. And then same thing for moment. We'll have the B variable to be able to vary this tensor. So we're given two different layups, a symmetric layup with just a laminate, and then one with half an inch honeycomb core, which the expectation here is that this will significantly increase the flexural stiffness of the panel and the ability to accommodate moment. So it'd be a good trade between the two, and kind of build upon some background on sandwich panels. And then from these, we'll calculate the ply-by-ply stresses and strains and compare to these three failure theories. So quickly, I wanted to give a little background on the theory. There's definitely, there's more, this is intended to be quick and not super comprehensive. So if there's a desire for more background, there's a lot of great resources on Professor Goyal's YouTube channel. So I'll quickly dive into it. So we're given modulus and Poisson measurements for the material, or allowables for the material. So we know these four properties in addition to Poisson's in the 2-1 direction, which can be calculated using this relationship. So from that, we want to relate stress to strain through the constitutive law. And that's done using to relate strain to stress, that's done using the S matrix, which is the compliance matrix. The inverse of the S matrix is the Q matrix, which is called the reduced stiffness matrix. So this is what you see here. So from that, you can find stresses in the global coordinate system, which I'll refer to as the XY system, from strains. And you can input to the matrix using these relationships here, which are again based on the material properties. So as I referred to before, those are in the global coordinate system. And as we know, and as we saw from the layup, each layer of lamina is at a different angle. So to find the effective stiffness matrix, you will need to perform a transformation from the Q matrix using the relationships that we reviewed above by using a transformation matrix. So that will give the as opposed to the 1-2 or principal directions, you'll be able to transform the stress and strain relationship in the lamina direction using a QBar matrix. So this is called the QBar matrix, and there's several different ways to there's a couple different ways to calculate that. There's relationships that I'll go into briefly in the Excel spreadsheet tutorial, and there's also invariant U inputs that you can calculate that will also yield this QBar matrix. So again, driving to the desire to find ply-by-ply stresses and strains. And a decent way to think about that is, so going back to the problem statement, we have found allowables for the lamina, and we want to have an opportunity to compare what we're getting in the actual design for a ply-by-ply stress and strain to these allowables, which are per ply. It makes it much more straightforward to be able to compare on that basis versus trying to like basically test your laminate with each different layup and develop strengths from there. So going back, so since stresses and strains in each ply vary through the thickness, it's convenient to define them about the midplane. And this is done through a summation integral of every ply through the thickness. And the reason stresses and strains vary is because of the angle change, or if you have a moment applied to your lamina. So you can see here, you're integrating through the thickness for each ply for stress for DZ, and then taking a summation for each ply. So this is one thing that can be a little tricky. That's important to understand. So as I stated before, it's convenient to find stresses and strains about the midplane for plate theory. So as you can see here, there's midplane. If you have a very thick lamina, it can lie somewhere in the middle of your lamina. But starting at the midplane, you effectively want to develop boundaries for each lamina or each layer. So here you have Z K minus 1 is the top of this layer, and then Z naught is the bottom. And then working up to the next one, you have ZK is the top of this layer, and ZK minus 1 is the bottom. So that might like come into play once I pull up my Excel sheet, but it can be a little tricky. So it's important to like think about it as you're developing a boundary for each lamina about the midplane. So referring back to the problem statement, you have a stress resultant and a moment resultant, and you want to relate that to the strains about the midplane and the curvatures. And that's done with something called an ABD matrix. And A is the summation of the product of Q bar, which was referred to before, of ZK, thinking back to like, the top of your length of each. So it's a summation. So it's through the thickness. So each lamina or each layer, and the top of the boundary of your lamina minus the bottom of the boundary of your lamina. So that'll give you like the effective thickness. And A is referred to as the extensional stiffness matrix, and it relates normal stresses and strains. Then A16 and A26 relate shear strain to normal stresses. B is called the bending extensional coupling matrix. And B12 or B16 and B26 relate twisting strains to normal stresses and shear strains to bending stress. And something to note is if you have a symmetric layup, these B matrix this B matrix will drive to 0, which is a nice check for your code. And this will indicate twist or bending in your laminate under load. Then D is referred to as the bending stiffness matrix, and it relates plate curvatures, or your curvatures here, to bending moments. So one thing to kind of cover in more detail is that your mid-plane strains, so like axial extension, in the longitudinal or transverse direction, and then you have curvatures. So under moment, your plate will develop a curvature to it. So you're able to measure you're able to calculate the curvature through these relationships. And then again, this is A, B, and D from these equations are a summation of the product QBar, which we referred to before, and then your Z, your lamina top and bottom as it relates to the midplane. So from this relationship in which we are given force, stress resultant and moment resultant, you're able to find your midplane strains and curvatures. But again, we're given the assignment to look at the failure theory for a ply-by-ply basis. So now we have the midplane, but we want to midplane strains and curvatures. We want to find the how that varies through the thickness or the stresses or the strains per ply that are rotated into the lamina coordinate system. So if you have a 30-degree ply, your principal direction will be rotated 30 degrees in your coordinate system. That's done. So we already calculated our midplane strains plus Z, which is the top, like depending on if you're going up from the midplane or bottom from the midplane, the top or bottom of your ply, or like the thickness times your curvature. So that will return the per ply strains in the global coordinate system, but we want it in the local or lamina coordinate system. So that's done through a transformation matrix. And then from that, we have per ply strains, and we want to develop stresses or find per ply stresses. So that's done through a constitutive relationship from your per ply strains in the global coordinate system and your QBar matrix. So at this point, I think it'll be useful to step into my calculations, and Excel is not the only way to do this. MATLAB or Python or your whatever you're most comfortable with. I think Excel is a decent way to visualize it, but definitely not the only way to attack this problem. So let's step into the Excel architecture or the spreadsheet architecture a little bit. So here I have the given material, AS4, S3501, as well as my material properties, E1, E2, G12, Poissons in the 1-2 direction, Poissons in the 2-1 direction, again, like through that relationship that we covered earlier. So that's the ratio of, that's the ratio of E2 to E1 times Poisson in the 1-2 direction. So again, back to the Excel sheet. So now we have all the material properties that we will need to develop our as an input to first your Q matrix. So again, this is the way I set it up. Not the only way to do that, but so here you have your layup. It's a symmetric layup with your ply thickness, and then your material for your material allowables for the or material properties for the lamina as given in the problem statement. then, and all these calculations are input to your ABD matrix, which we covered earlier. So here you have your laminate integral values. Pardon me for skipping around a bit, but so again, it's these three relationships right here. So you need zk minus 1 for each lamina, and then you need that relationship squared, or zk squared minus zk minus 1 squared, and then zk cubed minus zk minus 1 cubed to calculate your ABD matrix. So I've done that here. Again, your S matrix, which is your compliance matrix. Your Q matrix is the inverse of your S matrix, but you can also calculate your Q matrix directly from these material properties, which is effectively what I've done here, using the relationships discussed previously. So your Q matrix per ply, it doesn't, and you want to find your effective lamina stiffness matrix by using the transformation matrix to develop QBar. So you'll notice like Q doesn't change at all because it's all material based, but QBar does change based on the angle of your ply. So now we have QBar. Now we're able to find our ABD matrix. That's done by a summation of the products, which again, we can see here, QBar, summation of this product, through your thickness. So that, and as you can see, like the B matrices are 0 because the laminate's symmetric. Like if I were to change one of the parameters, B is no longer symmetric. The B matrix is no longer 0. So now we have our ABD matrix. We want to, knowing N and M, which are here, I have it under this loads label. We want to, knowing N and M and knowing our ABD matrix, we want to find the midplane strains and curvatures. So that includes taking an inverse of the entire ABD matrix, which is referred to as the ABD inverse matrix, and multiplying that by your N and M matrix to develop midplane strains. So now we have midplane strains, and the next step, and I also have related N and M. I have the given loads in the problem statement, but I've multiplied that by A for N and B for M to give me an opportunity to vary the loads based on if I can tell, if based on the failure theories, we can see that they're inducing failure. So the first thing I want to jump into, so again, now we have the midplane strains and curvatures, and we would like to calculate the per ply strain and transform that into the lamina or layer coordinate system. So you can see here, so I have the top and the bottom of the ply. And then I also have the thickness or the Z station where you are in relation to the midplane. So midplane 0, so around the midplane. And so you have like your overall thickness, and you start building up to 0.035 and building down to negative 0.035. So this will be done by this relationship here. So you have your midplane strains, and then you have your Z station. You multiply that by the curvatures to return your strains in the global coordinate system. And then in order to, then you would transform them into the local coordinate system. So now I have my strains in the global coordinate system, and then using the transformation matrix, these are rotated locally. So you can notice these are all These are all fairly similar under an axial load, and then they change based on angle because they're being transformed into from the EX to E1 or the global to local. One thing I did here that was convenient for visualization is I used the conditional formatting tool to color my plies or my strains green if they're passing, and you could also color them red if they're not passing. But that does present like a decent visualization tool, so you can vary A and B. But before I go, I will cover one more thing. So now you have strains in your in the ply or the lamina coordinate system, and from that you can as well find stresses in the global and local coordinate system, and that is done with your QBar matrix relationship here. So let's quickly jump into failure theories. Again, there's another lecture on this YouTube channel that goes into much more detail that I highly recommend watching. But we'll just, since they're being implemented in this spreadsheet, we'll cover them here. So maximum stress theory. So now you have your per ply stresses that we have developed from the classical plate, laminated plate theory. But you also are given allowables in the problem statement. So you have your longitudinal tensile strength and longitudinal compressive strength that's measured from testing as in addition to your transverse tensile and compressive strength, as well as shear. So that will help. And basically, like for each ply, you want to stay under your allowable, which seems very straightforward. And then for strain, you'll note that you can calculate strain theory or you can calculate your strain allowable. So E11T equals, jump back to the Excel sheet really quick. So you see I have the strain allowables down here, and all they are is, so you have X sub T, which was given, divided by E1, which will give you your strain allowable. Same with C, you have X sub C, which was given, and then divided by E1. And then in the transverse direction, you'll use E2 and so on and so forth. So that helps you develop your strain allowables. And same rule, you now have your strain allowable, and you have your per ply strains, and you want to stay under the allowable per ply. The third one is Hoffman, which is straightforward to implement for design, but it is an interactive theory. So as opposed to evaluating each, your E11, E22 in the tensile and compressive, or I guess better way to explain it is, instead of evaluating sigma 1, sigma 2, tau xy, or your shear stress, they do interact with each other. So this relationship is an interactive theory, and basically, if you're above 1, that shows failure, and if you're below 1, then this would show your design's robust. And here's a relationship between Hoffman predictions and then test values. You can see it correlates pretty well. So now we have, I have A and B, which again, are parameters to scale your stress resultant and moment resultant. And I can see here with A being 1, there are some exceedances by 128% in the E1 direction, or E1 strain, versus my E11T allowable, since it's all in tension. If it was in compression, then it would be compared to the E11C allowable. Then in the 2 direction, your strain, there again is additional like exceedances by 358%. So what we'll do here for strain is I'll take my max exceedance, which is 358%, and I will scale down A 8. Sorry, 3.58. Make that equal. And so again, that's just passing, and see the 100% here indicates that you're like riding up right against your allowable. So we'll do something similar for stress, and so that would inform like for your strain criteria, you could accommodate 27% of the load input before you induce failure. Similarly for stress, this would kind of lead me to believe that maybe the stress criteria is a little bit more conservative because you're showing failure and your center applies, but it looks like it's 103%. So you can vary this down additionally. Just make this 3.7 to make this simple. And then you see passing, and again you see you're like riding right against your sigma 2 allowable. So your transverse direction allowable. And then for Hoffman still is again the interactive criteria, and it still shows you're failing by about 50%. So you can again like play with these inputs a little bit. I just did 15% of the load. It looks like you're more than enough passing, so you could vary that up a little bit. And now you're failing. So it's a little bit of an iterative process here. So that was a load case for just the stress resultant, and now we'll start varying B. So B, you notice this laminate, it's very thin laminate, probably not super robust against moment. So B here, B was one, showing like massive exceedances, like 20,000%. So again, you can follow the same workflow and vary B in order to show passing for each stress-based criteria, strain-based criteria, and Hoffman. Then you could look at like 0.5, 0.5, and try to do a combined case for each of these three to develop some intuition about failure theories and like what load this layup could accommodate to pass. And then I think it was suggesting the problem that you plot A versus B for each criteria, or maybe make a table of A versus B to kind of show what the max load for each stress, strain, and Hoffman criteria would pass based on the failure theory. So pretty much there in the problem. I think there's one more part B, which is adding a core at the midplane of your layup and observe what results you find from there. So I think probably helpful here is to, let's see, let's try to find like let's make A 0 and B 0.05. And again, like you have to keep varying this load. But I guess what you could obtain from this is that this is very resistant to moment. So, very low moment, you're still showing some failure in some of your applies. So let's jump over to my second tab, which the only difference is now I have core in the middle, which I have a new ABD matrix. Again, following this workflow, I have an ABD inverse matrix. I now, with some load, I now can have midplane strains, which you can use the relationships discussed prior to find ply-by-ply strains and then rotate them into their coordinate system, and then same for stresses. So one thing to note here is that with core, you can accommodate much more load. So again, it would be following that same workflow. Maybe try to make this higher, showing failing a little bit. So maybe you want to lower this a little bit. But I think now that you have your spreadsheet set up, you can modify these loads. Develop like an A and B table or plot based on these three failure theories in order to compare the two layups. So one being a sandwich panel, one being laminate. And with that, I thank you for your time. Hopefully this was helpful. And yeah, enjoyed taking you through this.